Hey everybody, welcome back to the Meta Career Questions. Today I'm going to take a look at the missing mail problem. So the missing mail problem was quite difficult for me, but after 2 days of work, finally I found the solution. So let's get started. Let me make sure that I'm recording. Okay, so let me write down what the problem is. Go to the top. You just switch to pen. Move this out of the way. Okay, we're good. So missing mail. Ugh, missing mail. So here is what the problem is like. So we're, oh my god, just don't do that. Or is the 100% zoom? Oh, I guess I'm really zoomed in. Okay, there, whatever. Let me erase this. Erase this, very small. Okay. So, missing mail. So here's what missing mail is like. We're given an array of prices. So you're given an array of prices, let's say 10 to 864 or 46 I think is the example. So let me tell you what the problem is about. So there are n days, and on each day package vi, let's say on each day I, package vi arrives. So on this, you have a choice. Number one, pay C dollars and get all the packages in the room. Silver, so I can write in the room. Or choice two, leave the room untouched. And so then with probability S, the thieves steal all the packages in the room. Okay. So then the question is, what is the, assuming best strategy, what is the highest expected value you can get? So let me give you a couple examples when we might care about making this choice. So, I mean, there's some very clear examples. So let's just say we have this v equals 10, 2864, 46. And let's just say S, so C is equal to 1,000. So you have to pay $1,000 to enter the room, right? Clearly, you're never going to pay this $1,000 because the packages are worth $10, $2, $8. So never enter room. Enter room. So then the expected value is 0. So let's just say we have the same packages, but C is equal to 0. So it doesn't cost anything to enter the room. You can enter the room whenever you want, and it doesn't cost you anything. Then in this case, the expected value is, what is it? I think I have the wrong numbers, but 30. Why? Because you can just enter any day you want, and because the price, you just enter every single day, and the thieves can never. I mean, the S here doesn't matter. S here doesn't matter. There's an S, but it doesn't matter. You can enter any day, and because it doesn't cost anything, you can just pick up all the packages, so you get all $30 worth of the packages. So now, what if S is equal to 1 and C is equal to 3? So after every single day, the thieves with 100% probability break in and steal the packages. And then it would never make any sense to leave any package in there because the next day will be gone with 100% probability. So then this 10, right, you should always come in days when it's profitable. So if S is equal to, sorry, I put 1, I meant, yeah, no, S is equal to 1, C is equal to 3. So on day 1, when you have a package worth 10, it's profitable because you get $7. You have to pay $3, you get a package worth $10, so you get a profit of $7. But then on day 2, the package is only worth 2, and it costs $3 to enter. So if by entering, you would actually lose $1 net. So it's not profitable to enter on the second day. Then by the third day, the package from day 2 will be gone because the thieves steal it with 100% probability. Therefore, following the pattern, on day 1, we can get a profit of $1 of $7. On day 3, we can get a profit of $5. On day 4, we can get a profit of $1. And then on day 5, we get a profit of 3, which is whatever it is, 16, 17, 12, 16, yeah. So then we could also do, I think this would be the same. If the probability was 0 that the thieves show up, then you could just wait until the very end, and let's say C equals 3, you can just wait until the very end, and then, very easily, because the thieves are never going to steal the packages, you wait until the very, very end, you get 10 plus 2 plus 8 plus 4 plus 6, and on the last day you have to pay $3 to finally access the package. So hopefully this makes sense. And the S, it doesn't have to be between, it doesn't have to be 1 and 0, it can be any value in between. So that's where the obviously there's difficulty there. The cases of 1 and 0 are very easy examples. In the cases where the C is huge and small, also easy examples. What matters is the cases in between. So how do we go about solving this? So probably what you want to do, so there is let me just tell you about the easy solution, right? The easy solution is we start on day 0. We get a package worth 10. Let me just make sure. Let me copy down the exact problem. Just to, let's see, 10 to 864. That is, 864. 10 to 864. So I put the, I put 846. So 10 to 864. I know it was 864. So the obvious solution is to just try out every single possibility, right? So so we start here at I equals 0, right? And then what we're going to do is we're going to try taking the package right now, in which case our profit is 10 minus C. Add to that the expected value of starting from I equals 1. Starting from I equals 1. And then we can calculate this by doing the same thing, right? By saying, oh, this is going to split up into 2 more possibilities. Either we take package 2 or we leave it in. And then this is going to split up into 2 more, and this is going to split up into 2 more. And the number of possibilities you have to end up looking at is 2 to 5, which is 32. However, yeah, so also to make it easier, when you decide to keep a package, so let's just say instead of deciding to take the package, you decide to leave the package in the room to try to pick it up a future day, then you can imagine it as if the next package, so basically leaving a package in the room, a package in the room is the same thing as the next package having value vi plus 1. So that's the value of the old package, plus vi, so that's the package of the one that you just left in the room, multiplied by 1 minus s, right? So the thieves went in and potentially stole the package, so its value has on average decreased by on average is 1 minus s, expected value, right? Like with probability. I mean, we can say this: the expected value of package vi is with probability s, the expected value is 0, so that's when the thief stole it, plus with probability 1 minus s, the package is still alive, Right out of room, vi. So therefore, this is 1 minus s times vi, right? Expected value. So the point I was trying to make here is that leaving a package in the room is the same thing as the next package having value this, right? So when we do this, when we do like this search, when we go down a path where we just left a package in the room, we can set the element temporarily, the array, to, we can set the array vi plus 1, set it temporarily to plus equal to vi v of I times 1 minus s, and then when we're done with the calculation here, we can unset it, right? vi plus 1 is equal to the old value of vi plus 1. So, however, this requires looking through 2 to the 5 solutions, and our upper bound for n, the number of packages, can be as high as 4,000. So 2 to the 4,000 is pretty much so big that, you know, this is never going to work. This is never going to work. So we need to find a way to break down the amount of work we need to do. And obviously this looks like dynamic programming. So let me try to motivate why we could break down the amount of work. So here are days: 10, 2, 8, 6, 4. So now imagine for a second that I knew that I was going to pick up the package on day 10, right? Sorry, I drew an hour, but 100% there's going to be 0 packages starting from here. So 0 packages. What does this mean? This means that we have like a blank slate right here. I don't know if I'm making any sense, but then when we try to calculate the value, you know, I don't know how to explain this well. Yeah, basically when we, or let's just say let's draw a line right here instead. So imagine that we just picked up whatever package is here. We're trying to calculate this option where we just went into the room right here. We just went into the room. So we have a completely blank slate. So what is our strategy for how to deal with these last 2 packages is now completely free from past, right? Because we have a completely blank slate. So if we try to calculate the optimal strategy here, we can reuse the how we dealt with these last 2 packages. We can reuse this computation regardless of what we did with the first 3 packages. Regardless of what we did with the first 3 packages. And you know, if we did this 2 to the 32 solution, then, or 2 to the 5 equals 32 solutions, if we went through all of them, we would end up actually having to recompute what we do with these last 2 packages, assuming that we just picked up many times. We'd have to recompute it. I don't know how many times, but lots of times. The naive strategy recomputes many times. So this is really bad. It's really it's not very efficient. So what we can do instead is well, here is my solution. So we can try to reconceptualize the problem instead into chunks. And what do I mean by chunks? So I'm going to take my my array here, 8, 6, 4, and I'm going to break them up into chunks. So here's my step 1. So I'm going to break this into chunks of 1. So here's my chunk of 1, here's my chunk of 2, here's my chunk of 3, here's my chunk of 4, here's my chunk of 5. Okay? And basically I'm trying to solve this problem, just this problem. Just imagine I only get one package and it's a 10. So if C equals 3, like in most of the examples given, then your profit that you can get is here is 7. Here, assuming this is the only package you ever get, the profit is 0, the other is 5, the profit is 3, and then the profit is 1. Okay? So that's assuming that it's the only package. So now for step 2, I'm going to look instead at chunks of 2. So I'm going to look at a chunk of 10 and 2. I'm going to look at a chunk of 2 and 8. And then I'm going to look at a chunk of 8 and 6. And then finally, I'm going to look at a chunk of 6 and 4. I realize there might be other ways to do this dynamic programming, but this is the way that seemed most straightforward to me. So now here is so my question to you is, how many ways are there, how many possible strategies are there to solve this problem of 10-2? Well, you can either take on the first day, right, and then take on the second day, or you can you can either take on the first day and then do whatever is right here, or you can leave this package and then do whatever is right here, right? So then let me just write down the possibilities for this. So let's just say the profit of, the way I say it, I think is 0 to 1 is equal to the maximum. So there's two possibilities here. Either we leave the package in either v of 0 times 1 minus s plus v of 1 minus c. So we left the package in for 1 day, and we added the second package in, subtracted c, because we try to see, I mean, obviously this is max of this. It might not even be profitable. So 0 to c. And then the second possibility is that we took the package on day 0, v0 minus c, plus the possible profit 1, 1. So basically what I've done is I've broken this problem of 2 into a problem of something, and then something that requires a solution from step 1, which in this case is 0. And then now if we take a look, if we try to do the step 3, which is 3 packages, 10, 2, and 8, the profit from 0 to 2, or maybe, yeah, I think the way I set this up, I mean, I don't know, the bounds don't really matter. I mean, 0 to 2, 2 inclusive, is equal to, so we could either hold for all 3 days. So v0 times 1 minus s squared plus v1 times 1 minus s plus v2 minus c, or, so the max of this, or we could basically hold for 2 days instead, v0 times 1 minus s plus v1 times 1 minus c plus the profit of 2, 2. Or we could take only today's package, v0 minus s, and obviously all these are max of this 0 because it might not even make sense to take this, plus the profit from 1 to 2. So you can see I broke it down into chunks, and then a solution to a future problem, you can write it in terms of solutions to your previous problems. You look at all the possible things that you might do and try to write it in terms of that. Let me make sure I'm still recording. Yes, I'm still recording. So, so what does this loop look like? For chunk size in, we start at 1 and we go all the way to n. Then we have to do this for every single one of these chunks, right? So for j in, let's say 0 to n minus chunk size, and then there is also an inner loop here. We need to generate these possibilities. So for a chunk size of 1, there are 2 possibilities. For a chunk, for chunk size of 2, there's 2 possibilities. So there's going to be generate chunk size probabilities, which is a lot. So what is my verdict on the solution? It is too slow, unfortunately. So this is an inner loop. It has to happen n times. So while it's not exponential, depending on n, it's n times n times n. So n cubed, which is still too slow. It is too slow. It is too slow. You know, I wrote out this entire dynamic programming solution, and it's still too slow. And you can write it like you know, other ways, but it's still too slow. So what is even with some optimizations that I did, so what is the actual solution? The actual solution is that you don't need to, so here's what I realized today after all this time, is you don't need to compute the expected value, compute the optimal strategy for every chunk. You don't. So let me give you an example of a chunk which 10 to 864 that we don't need to compute the expected value of. I think this one, 86, or the best strategy, the best profit. We don't need to compute this chunk. It turns out we don't. So let me try to reframe the problem. So here, when I rewrote the problem, suddenly became a lot more clear. Which ones do we actually need to compute? Which ones do we not need to compute? So we're trying to find the maximum possible profit from, let's say, 0 to n. And this n is exclusive. I know it was inclusive before up there, but I wrote it now, so it's exclusive. So what are the, so this is what we want. This is our final thing that we want. There are no packages before here. So by profit, I mean, what is the definition of profit? This is assuming no packages before start. What is the maximum dollars we can make with the best strategy? With the best strategy. Okay, start ending at n. Ending at n. So this is important, assuming no packages before start. So so what is this actually equal to? Well, there are a lot of possibilities. So either we can take the, so when we're trying to break this down into smaller problems, right? Let's say the maximum of, we can either take the first package, right? So V0 minus C plus profit starting at 1 to n, right? Makes sense? And then the next possibility is we leave the first package in there for a day, and then we pick it up on the second day, right? V1 minus C plus profit 2n, right? And now we keep going with this pattern. So we keep leaving the packages in there. The final one is just V0 times 1 minus s to the probably n minus 1 plus dot 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 vn minus c, and that's it. So those are all the possibilities, right? So now you might ask yourself, okay, so which profits do we actually need to know to calculate this expression? Well, I can tell you, it's profit 1 to n, profit 2 to n, dot dot dot, profit nn, right? Which is, I think this one's 0 because the numbers are the same, probably. So what is profit 1 to n? Which profits do we need to calculate profit 1 to n? Well, pretty easy. profit, right? If we follow this, if we apply the same formula, but to profit 1 to n, which ones do we actually need? 2 to n, dot, 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 profit n to n. Make sense? So, and this profit 2 to n, how many profits do we need? We need profit 3 to n, dot, dot, dot. And the magic thing about this is that this profit 2 to n, we also need it here. And this profit 3 to n, we need it here and here. So how many profits do we actually end up need? Which ones do we actually end up needing to calculate? It's this one. This is the first one we need to calculate. Then we need to calculate profit n minus 1 n. Then we need to calculate profit n minus 2n. And dot, 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 all the way down to profit 0n. These are the only ones we need to calculate. So the example I gave above, where we look at a profit between two values, assuming that it's up to package 6 and that there's no packages left in before 8, we don't need this. We don't need this because this expression doesn't require it. So I was basically in my previous dynamic programming solution where I looked at every single chunk. This work isn't needed. It's just not needed. We only need to calculate these ones. And these ones are very easy to calculate. So profit n to n, this is probably 0. Profit n minus 1 to n, this is probably just take the package or not. So v n minus 1 time minus c. And then this profit n minus 2 is according to this, right? It'll be like probably like 2 possibilities. So yeah. So knowing all of this, let me look at my solution. So here it is what I did. So I defined something called a stopping point. I also made this more efficient. So this will be the, you see how when you calculate these things, you need to calculate these Vn, this entire term. So I made this more efficient by basically memorizing these values, and then when I need a bigger value, I multiply the previous one times 1 minus s and add the new package in. So that's why I needed this big function for that. And then I also had special cases for this because it's faster when s equals 0 and s equals 1. But then so what I did is I defined a stopping point. So the stopping point is when we are going to probably, let me see. So some starting point, profit, stopping point, and I think I flipped it around. Did I possibly flip it around? Some profit, stopping point, end. No, I didn't. So my stopping point is when are we going to sell the packages that we have been accumulating from the beginning. Let me write that down. So stopping point is when do we sell the packages that we have been accumulating from the beginning? When do we sell packages that we have been accumulating from beginning? So in the case here, the stopping point is 0. In the case here, it's 1. In the case here, it's n, right? So I do this. So here are my possibilities. This is all of these possible, and I take the max across all of them, right? Here's the max across possibilities. So profit starting from stopping point to the end. So that's a recursive definition, the profit 1, or profit 1n. And then and then here is our sum, this v1, assuming that we're holding packages for up from start to stopping point, minus c. So very straightforward. This is all we need, and then at the end we return profit from 0 to n. So with this, I can show you. No, don't go to the next puzzle. Go back. Missing mail. There we go. I guess it doesn't. Oh no, it's the submit buttons here. So I'm gonna press submit, and as you can see here, the n is 4,000, right? So there's potentially a lot of packages. So we do need an efficient solution here, and it's going to work. It will work. There we go. You see? Very nice. So that about wraps up this conversation. Hopefully I was recording at the end. Yes, I was. Merry Christmas to everybody, and I'll see you in the next one. Thank you.